There's an attack called differential power analysis, where basically you measure the power consumed by the card over many runs of the encryption algorithm. And as long as there's any even small dependence between the amount of current consumed and the bits of the secret key, basically that dependence will show up after enough runs of the encryption algorithm, and as a result you'll be able to completely extract the secret key. Okay, so these attacks were actually discovered by Paul Kocher and his colleagues up at Cryptography Research, and there's actually a fairly large industry devoted to just defending against these power attacks. As far as timing attacks are concerned, I want to mention that these are real. They're not just about smart cards. For example, you can imagine a multi-core processor where the encryption algorithm is running on one core and the attacker code happens to be running on another core. Now, these cores actually share the same cache, and as a result, an attacker can actually look at the exact cache misses that the encryption algorithm incurred. It turns out that by looking at cache misses, you can completely figure out the secret key used by the algorithm. So one core can essentially extract information from the other core just by looking at cache misses. So implementing these block ciphers is actually quite subtle because you have to make sure that the side channel attacks don't leak information about your secret key. Another type of attack that's been discussed in the literature is what's called a fault attack. So here, basically, if you're attacking a smart card, you can actually cause the smart card to malfunction, perhaps by overclocking it, perhaps by warming it up. Essentially, you can cause the processor to malfunction and output erroneous data. It turns out that if during encryption there are errors in the last round of the encryption process, that the resulting ciphertexts that are produced are enough to actually expose the secret key K. It's quite an interesting result that, in fact, if you have any errors, if you ever output a wrong result, that actually could completely compromise your secret key. So, of course, the defense against this means that before you output the result of your algorithm, you should check to make sure that the correct result was computed. Now, of course, that's non-trivial, because how do you know that the error didn't happen in your checking algorithm? But there are known ways around that. So basically, you can actually compute something 3 or 4 times, take majority over all those results, and be assured that the output really is correct, as long as not too many faults occurred inside of your computation. These are attacks on the implementation. I hope these examples kind of show you that not only should you not invent your own block ciphers, you should never even implement these crypto primitives yourself, because A, you have to make sure there are no side channel attacks on your implementation, and B, you have to make sure that the implementation is secure against fault attacks. Okay, so instead you should just use standard libraries like the ones available in OpenSSL and many other libraries out there. So don't implement these primitives yourself, just use existing libraries. Alright, so now I want to turn to kind of more sophisticated attacks on block ciphers, and I'll particularly talk about how these attacks apply to DES. Okay, so these attacks were discovered by Biham and Shamir back in 1989, and I'll particularly describe a version of the attack discovered by Matsui in 1993. So the goal here is basically, given many input-output pairs, can we actually recover the key better than exhaustive search? So anything that runs better than exhaustive search already counts as an attack on the block cipher. Okay, so the example I want to give you is what's called linear cryptanalysis. And here, imagine it so happens that C is the encryption of M using key K. And suppose it so happens that if I look at a random key and a random message, somehow there's a dependence between the message, ciphertext, and the key bits. In particular, if I XOR a subset of the message bits, so this is just a subset of the message bits, if I XOR that with a certain subset of the ciphertext bits, so these two the attacker sees. The attacker has the message and the attacker has the ciphertext. And then you compare that to an XOR of a subset of the key bits. Now, if the two were completely independent, which is what you'd like, you definitely don't want your message and your ciphertext to somehow predict your key bits. If the two are completely independent, then this equality will hold with probability exactly 1/2. But suppose it so happens that there's a bias, and this probability holds with probability half plus epsilon for some small epsilon. It so happens that, in fact, for DES, there is such a relation. The relation holds specifically because of a bug in the design of the 5th S-box. It turns out the 5th S-box happens to be too close to a linear function, and that linear function, basically, as it propagates through the entire DES circuit, generates a relation of this type. You notice this is basically a linear relation that's being computed here. So this small, tiny linearity in the fifth S box generates this relation over the entire circuit where the epsilon is tiny. Epsilon is 1 over 2 to the 21, and I wrote down what that is. So the bias is really small, but nevertheless there is a bias using these particular subsets of bits. Now I'm not going to show you how to derive this relation, or I'm not going to show you even what it is. I'll just tell you how to use a relation like this once you find it. Okay, so here's our relation that we have, and the question is how to use it. So with a little bit of statistics, you can actually use an equation like this to determine some of the key bits. And here's how you do it. Suppose you were given 1 over epsilon squared message ciphertext pairs, and these have to be independently random messages and the corresponding ciphertexts. What you would do is you would use the formula above. In fact, you would use the left-hand side of the formula above to compute this relation between the message and ciphertext for all the pairs you were given. Now, what do you know? You know that for half plus epsilon of these values, you know that these things will be equal to an XOR of the key bits. So if you take majority over all the values you've computed, it turns out it's not so difficult to see that in fact you'll get the correct prediction for the XOR of the key bits with probability 97.7%. In other words, if this relation happens to be correct more than half the time, then the majority will be right. And because there's a bias, there's an epsilon bias, the probability that you will be correct more than half the time is in fact 97.7%, in which case the majority in fact will give you the correct XOR of the key bits. Okay, so this is kind of cool. Within 1 over epsilon squared time, you can figure out an XOR of a bunch of key bits. So now let's apply this to des. So for des we have epsilon, which is 1 over 21, which means that if you give me 2 to the 42 input-output pairs, I can figure out an XOR of the key bits. And now it turns out, I'm not going to exactly show you how, roughly speaking, using this method, you don't just get 1 key bit. In fact, you get 2 key bits. You can kind of use this relation, one's going in a forward direction and one's going in the backwards direction. So that gives you 2 XORs of bits of the secret key. Okay, so that's 2 bits of information about the secret key. And then it turns out you can get 12 more bits because essentially you can figure out what the inputs are to the fifth S box. Okay, so I'm not going to exactly show you how, but it turns out you can get 12 more bits, which is a total of 14 bits overall. So now using this method, you've recovered 14 bits of the secret key, and of course it took you time 2 to the 42. Okay, so then what do? Well, so the rest of it is easy. Now what you're going to do is you're going to do exhaustive search on the remaining bits. Well, how many remaining bits are there? Well, there are 42 remaining bits, so the exhaustive search would take you time 2 to the 42. So what's the total attack time? Well, the first step of the algorithm to determine the 14 bits took 2 to the 42 time, and the remaining brute force search also took 2 to the 42 time. So overall, the attack took 2 to the 43 time. Okay, so now this is much better than exhaustive search. Within 2 to the 43 time, we broke des, but of course this required 2 to the 42 random input-output pairs, whereas exhaustive search only required 3 pairs. Okay, so this is a fairly large number of input-output pairs that are needed, but given such a large number, you can actually recover the key faster than exhaustive search. Okay, so what's the lesson in all this? The lesson is firstly, any tiny bit of linearity, basically in the fifth S box, which was not designed as well as the other S boxes, basically led to an attack on the algorithm. Okay, a tiny bit of linearity already introduced this linear attack. And I want to emphasize again that this is not the sort of thing you would think of when you design a cipher. And so again, the conclusion here is there are very subtle attacks on block ciphers, one which you will not be able to find yourself. And so just stick to the standards. Don't ever design your block cipher. Okay, so that's all I want to say about sophisticated attacks. Now let's move on to the last type of attack that I want to mention, which I'll call quantum attacks, which are again these are generic attacks on all block ciphers. So let me explain what I mean by this. So first of all, let's look at a generic problem. It's a generic search problem. Suppose I have a function on some large domain X that happens to output either 0 or 1. And it so happens that this function is mostly 0, and there's like maybe one input where the function happens to evaluate to 1. And your goal is basically, find me the input where the function happens to be 1. Maybe there's only one such input, but your goal is to find it. Well, so on a classical computer, what can you do? The function is given to you. It's given to you as a black box. So the best you can do is just try all possible inputs. So this is going to take time, which is linear in the size of the domain. Now it turns out there's an absolutely magical result that says that if you build a computer that's based on quantum physics as opposed to classical physics, you can solve this problem faster. So let me explain what I mean by this. So first of all, in the 70s and 80s, it was observed, I think it was actually Richard Feynman who observed this initially, that said that it turns out to be very difficult to simulate quantum experiments on a classical computer. So Feynman said, hey, if that's the case, maybe these quantum